welcome back. We are going to start a new topic. It's a thermodynamic properties from volumetric data. Okay, as we have already discussed earlier, that we cannot measure enthalpy, entropy, and all this free energy directly. Okay, so these are not measurable quantities directly. However, we can measure the difference between them. What we have accessible to experimental data are basically in properties or in the form as in temperature, volume, pressure and heat, or that is heat capacities. Okay. So, these are the data which we can measure. Okay. And the interest is basically we want to find out want to measure changes in thermodynamic functions such as the properties such as enthalpy, entropy S at constant temperature from P, V, T and given composition data. Okay, so these are the data which may have, and our interest is to find out the changes in these properties. Okay. Now, what are the typical data which are usually available? So, there are two forms. So, the data is usually given in two forms. Okay. One is V as a function of T, P, N. Now, this is easier to measure. Okay. Another case is pressure as T, V and N. Now, this is easier to model. Okay. So, that means this second one is basically we can make use of ideal gas, for example, or in some equation or state we can use it, and thus we can make use of this data to model such system. Okay. So, let me just start first with thermodynamic properties. With Tp as in here as independent variables. So, let me start with this first. And what is our goal? Our goal is basically to express fugacity in terms of experimental obtainable properties. So, to express fugacity in terms of experimentally obtainable properties. Okay. Now, as we know from the Maxwell relation that at a constant temperature and composition, we have the following expression for the enthalpy in differential form. Okay, and as well as we can write entropy in differential form okay. So, this is directly from the Maxwell relations, the second one particularly. Now, we can integrate this expression. So, if I integrate the enthalpy expression, so we have this minus H. So, we are integrating from pressure 0 to P. So, P equal to 0 and constant composition. So, this is going to be 0 to P V minus T del V by del T at constant pressure, and here is going to be dP. Okay. Now, this is nothing but at a 0 pressure we can approximate this to be an ideal gas, and thus in that case the partial molar enthalpy is nothing but molar enthalpy. So, we can write this expression as summation Ni Hi 0, where this is nothing but the molar enthalpy of pure I as an ideal gas at temperature T. Okay. So, we can rewrite this expression, and I can get the following. So, I can take this term to the right hand side, and this is the expression of enthalpy at temperature Tp with the mole compositions here. Okay. Now, similarly, the way we have done for enthalpy, we can also try to integrate the case for entropy. Okay. So, let me try to do that here. So, if we integrate this second expression which we have written based on the Maxwell relation, we get S Tp and N minus S T P 0 some P 0, which of course could be close to 0. Okay, and this is from P 0 to P minus del V by del T at constant pressure and keeping N constant dP. Okay. So, note that this is simply the integration of this expression. Okay. Now, what we can further do is we can take this right hand side. Okay. So, this is our right hand side. Okay, and this expression comes here, and I am going to now play with the term such that I am going to insert anti-R by P minus del V by del T at P, okay, dP, and then since we have added here, I am going to subtract this term, considering that this is going to be a simply okay. Okay. The reason we have done this because this term is nothing but the term corresponding to the ideal gas, okay, and let me just write that. So, we can go back to the original definition of this entropy again in the differential form, and now assume that to be for ideal gas mixture. So, ds is minus del V by del T at P n dP. Now, assume this to be for ideal gas mixture. Okay. Now, for ideal gas mixture, of course, the equation of state we can write as V can be replaced by simply anti-R T. So, here V is nothing but Tp. Okay. So, when you are going to differentiate with T, you get nothing but minus anti-R P by dP. All right. Okay. So, if you integrate this, we get the following from, let us say, from P 0 to P. Okay. This is going to be S of I G M Tp n minus S of I G M Tp 0 m. Thus, this expression is nothing but this difference in the entropy in ideal gas mixture from P0 to P. Okay. So, I can now replace this. Okay. So, my left hand side expression is still STP n minus STP0 n. Okay. And my right hand side expression now is plus SIGM TP and minus SIGM TP0 and okay. Now, as I said, P0 now you could be anything. We can take it to be now. If we consider P0 tending towards 0, okay. So, in this case, of course, the ideal gas mixture at pressure P0 should behave as an ideal gas mixture. So, STP0 and is nothing but SIGM TP0 n. Okay. So, it is basically ideal gas mixture, the entropy. Okay. So, if that is the case, then of course, this and this term should cancel each other because these are the same term, because this will behave like an ideal gas at P0 tending towards 0. Okay. So, what remains now is STP n is 0 to P okay, plus SIGM at P. So, this is the term which we have. Okay. Now, many times we take reference values corresponding to 1 atmosphere. So, let me just rewrite this expression of delta S or S with reference to the pressure at 1 atmosphere, and then we can simplify this with the data corresponding to 1 atmosphere. Okay. So, what I was saying is basically that if I can write down, instead of taking P0 as 1 as 0, we can also consider for an ideal gas, okay, as 1 atmosphere. Okay. Now, the right hand side expression remains the same because the ds integration here would be simply minus NTR for an ideal gas divided by P dP, but instead of P0 we have 1 to P, okay, which essentially means I can rewrite this expression as minus NTR ln P by 1 atmosphere. Okay. Now, NT is nothing but summation of Ni, so I can also write minus R summation Ni for I equal to 1 to m ln P 1 atmosphere. Okay. Okay. So, what we are going to do is we are further, so I can make use of the expression of SIGM which we have evaluated earlier. Particularly for 1 atmosphere. So, this is going to be summation NISI. So, I am just getting this value directly from our earlier expression minus R summation Ni and Yi. Okay. So, now I have this expression. So, let me say this is expression number 1, this is 2 and this is 3. Okay. So, if we combine this, okay, what we are going to get is S of T P summation Ni summation sum of S of Tp for mole compositions here or number of moles here. Now, this should be equal to this term, okay, which we have written with respect to 0 P NT R by P minus del V by del T at constant pressure, okay, dP. Okay. Now, we are going to use this expression here from here, which depends on this pressure P1, which is accessible pressure. Okay, so I am going to take this on the right hand side, and then I am going to use this expression, this. So, we can combine this expression. So, let me write it here, minus R summation Ni ln Yi P by 1 atmosphere, okay, plus summation Ni Si 0. Okay. So, what we have done is nothing but we have combined this two, this one, and this term we have written as simply Ni Si 0, where Si 0 is nothing but molar entropy of pure I as an ideal gas at T and P is equal to 1 atmosphere. Okay. So, this is the expression we got. Okay. So, I have remember that I combined this term and this term to get this term, okay, and this term is nothing but this term. So, thus this expression plus this expression together is this two expression. So, this is a simpler form of the entropy. Now, given these two terms which we have calculated for enthalpy and entropy, now you can extract other thermodynamic properties such as internal energy, Helmholtz free energy and Gibbs free energy, okay, with respect to this volumetric data in terms of independent variables V and T. Okay, so let me just summarize this expression instead of deriving it. Okay, so we have U is equal to H minus PV. Okay, so since H we have already calculated, okay, or derived here. Okay, this is the H value. So, we just have to add here minus PV. Okay, so this term minus PV plus this term. Okay. Now, remember again, so this is U minus PV. Similarly, we can get A, which is H minus PV minus Ts, and then you have this G, which is H minus Ts. Okay. Now, I can write this more explicitly because I will be using this G expression in calculating chemical potential. So, let me write down G, that what would be the G? G is nothing but H. First I am going to write this H 0 to P V minus NT RT divided by P, okay, and the other term which is NiHi 0 will come somewhere here, okay, plus this Ts term, okay. So, this will be RT summation Ni ln YIP divided by 1 atmosphere, okay, and minus TSI will come here, okay. So, again this is the P term. So, what happened here is basically this two terms got cancelled, this term and the corresponding if you look at here V term V minus T V by T, this and this term got cancelled. So, what remained was NTR P and V term, okay. So, this is how you are going to get this expression G. Now, this expression you can make use in order to calculate the chemical potential. Okay. So, what is the chemical potential? Of course, chemical potential is the partial or molar derivative of Gibbs free energy. So, I am going to define here del G by del Ni Tp for all other J's and J's constant. Okay. Now, we can evaluate this expression further. So, let us take a derivative of this. So, what is partial derivative of G with respect to Ni? Okay. Remember, this Nt is summation Ni. Okay. So, del G by del Ni is going to be 0 to P del V by del Ni minus R T by P. Okay, since Nt is equal to summation Ni, when I am going to take the derivative with respect to Ni is going to be 1 plus R T summation del Ni. Now, here since I am using I, since I is 1 to m, and here this is a specific I, so I am going to change this to Nj. Okay, ln YIP by 1 atmosphere plus summation Ni will be 1. If you take the derivative of this, this will be 1. So, what remains is basically Hi0 minus Ts(I0). Okay. Now, I won't derive this part, this is a bit tricky, okay, but this you should be able to show that for I is equal to not equal to J, del N by del Ni Nj ln YIP by 1 atmosphere is simply minus Yj, and when I is equal to J, this would be Ni ln YIP 1 atmosphere is going to be simply ln YIP by 1 atmosphere plus 1 minus Yi. Okay. So, of course, this can be separated into two parts, one with this and the other with this part. Okay. All right. So, if you do this exercise, what you get is that summation of this is nothing but, or the derivative of this is nothing but ln YIP 1 atmosphere is equal to 1 minus Yi minus sum of Yi for all I not equal to J, and of course, this is nothing but simply this should be plus. Okay, so this is nothing but 1 minus Yi, so this cancels out. Okay, so what remains is this. Okay, so thus we have an expression of mu I is equal to del G by del Ni Tp which is 0 to P. This is nothing but partial molar volume minus RT by P dP plus RT ln YIP by 1 atmosphere plus Hi0 minus Ti0. Okay. So, this is the expression which we got. Now, the last leg of this derivation is to connect this expression to the fugacity. Okay. So, let us do that. Now, from fugacity definition, we have RT ln Fi by Fi0. Okay. Now, suppose that the standard state which we are using here is so this is a standard state chemical potential. So, we consider this as ideal gas of pure I at T and P is equal to 1 atmosphere. So, let us assume this as a standard state. In that case, mu I is nothing but, for the pure, nothing but small g I, which is going to be h I 0 minus T I 0, considering this to be these conditions for the pure case. Okay. And of course, considering the standard state is an ideal gas, F I 0 is going to be P 0, which is nothing going to be 1 atmosphere. Okay. Now, given this, we can plug our mu here. Okay. So, R T ln F I, because F I 0 is equal to 1, this is going to be 0 to P V I bar minus R T by P dP, okay, plus R T ln Y I P. So, I am removing this 1 atmosphere because that gets cancelled by F I 0, and mu I 0 gets cancelled by H I minus T I. So, what remains is only this term. This further can be simplified as T ln F I Y I P 0 to P V I bar minus R T by P dP. Okay. So, I have taken out this expression here, and this comes out in the denominator. So, I have this expression for fugacity, or in this case it is going to be fugacity coefficient, this ratio which relates to the volumetric property as V I bar minus R T by P integration from 0 to P dP. Okay. I will stop here, and then I will continue this exercise by taking certain assumptions and connecting with some experimental information or data. Okay. So, I will see you in the next lecture.